Okay, I'll share my screen. Let me know if you can if you can see my screen. All right. Okay. This is, I want to say, the sixth week of the mission semester course. And today غنطاك لي واحد التوبيك اللي هو شويه I don't think it's gonna bring anything new من غير داك الشيء اللي قريناه من قبل, but it'll try to bring a lot of things together. نحاولوا نشوفوا كاع داك الشيء اللي قرينا, نحاولوا نشوفوا شنو ماشي شنو نقدروا نصايبوا به مي شنو داروا به الناس في 2003. And hopefully we can learn some things along the way as to how to put things together. دوك البيلدينغ بلوكس اللي تعلمنا في هاد الخمسة السيمانات اللي فاتوا, how to put can we put them together باش نصاوبوا شي حاجة اللي هي practical. Alright. So the plan for today is like we'll cover a bunch of terminology and concepts. Some of them غتشوفوه, well, I don't think غتشوفوا أول حاجة أول مرة, but it'll be like a nice refresher about شنو هما الحوايج اللي شفنا along the way. And we'll talk about GFS as the example of a distributed file system, and then I'll maybe give you some homework to do. كيما العادة, like فاش يكون عندكم questions, that just use the raise hand tool, and I'll hopefully be monitoring chat along the way, although it gets a bit distracting. Okay, let's go with terminology. هضرنا على load balancer, I guess at some point, and I just want to give a refresher about our load balancer, and that everybody knows what a load balancer is. So it's a component, it's a software component that is usually responsible for like spreading traffic across multiple servers. We usually like to have it as an entry point into our system. Users into a system ديالنا, they don't have to know باللي عندنا an authentication service واللي عندنا a couple of storage components and then yet 300 other microservices. You just know about like one entry point, and then just send it requests, and then the load balancer will take care of all of it, authentication, like session management, forwarding the proper HTTP requests, and then like distributing load accordingly. It can have, since it's the single entry point of component of the system, it's a great location where you can put a bunch of your cross-cutting concerns, which is like end-to-end monitoring and then logs and anything else that you want to track it across all the system. And بزاف نتاع flavors in terms of like algorithms. Some of them work better than others depending on the use case and network topology, and then the actual infrastructure topology. Round robin, like least connections, least response time, IP hash, and then a bunch of others. They can also be done as you can also find like a load balancer at the client side. Like there are things that we call fat clients or thick clients, which are like client libraries that contain like logic information, and they're not just stubs that call into like other systems, but they also have a bunch of logic that keep track of which are the connections that are alive, which are the available clients, and then they can also have logic to select which client should I talk to based on some predefined logic or external system. And this can be like your load balancer could be like potentially your single point of failure, because it's the central point that everybody calls. So you should be very careful about like having it super reliable and having standby ready load balancers that can replace it, since it's just usually it's just a compute heavy resource. So like replacing it is not super expensive nor super hard. So you can always like replace it on the spot. The problem is detecting that the load balancer is down before your users do, so that the failover is kind of automatic and you don't your users don't detect any downtime. Okay, load balancer. Are we clear on this? Does this make sense? Elena? If this makes sense, do thumbs up. If it doesn't make sense, don't do anything. اوكي خليل بوحده هو اللي فاهم. اوكي سعد فاهم. Who else? اوكي ولا كلشي كيقلب على فين كاين هاد اللعيبه. Okay, cool. I guess like load balance. I'm not gonna spend a lot of time on load balancer because it's like one of the thing that everybody's familiar with. And if you're not, and if you have any questions, please pause here and then ask me questions because it's essential that you understand what a load balancer. But you have to understand load balancer because this is the closest thing that you'll actually use in your day-to-day job. Okay, moving on. Yeah, an index. An index is an index. شكون عمرو اسمه index؟ شكون ما عمرو اسمه index؟ Yeah. Thumbs up. رضا بغيتي تقول شي حاجه ولا جست ما عمرك سمعتي باندكس؟
لا ما عمرني سمعت بالاندكس. انا سمعت بالاندكس ولكن واش اندكس شي حاجه اللي ما
واخا
شي حاجه اللي ما عرفتهاش.
اوكي ذاتس جود. شنو هو اندكسين؟
all I know about the indexing هو انه واحد الواي اللي الا كانت عندنا واحد التيبل اللي فيها بزاف ديال الكونتنتس وباش نلقاو هذاك الكونتنتس it's gonna take a long time في الداتابيز ديالنا. الاندكسين تيكري واحد التيبل اخرى اندر ذا هود اللي فاش كنقلب على واحد الحاجه محدده تمشي يقلبوا بداك الاندكس. ولكن هاو داز ات ورك ولا واش زعما داكشي بلو بروفون ما عرفتش.
Yeah. So indexing is kind of like this. But it doesn't have to just apply to databases. It's a way to, usually it's used to speed up lookups. You have, as again, like a software component, storage systems, mainly databases, and it's used for to speed up like reads. So in most cases, an index is like pages. Like every storage system has some sort of page semantic. Like so, a database is key value stores, whatever. We'll store data on disk in sort of pages. And ideally, if the clients send us read requests, I want to read some key, right, from this given like I want to read this key. If you don't know finkain dakal key, you'll have to open every page file, or every file that contains your pages. It could be like one page per file, or whatever your layout is. But you have to keep opening these files and then read the information linking of those files to try and match that key. And then once you find that key, you get the associated value, which is usually a tuple of values or a single value if you have like a single key value store. And then that's get transferred back to the client. And if you think about doing this like in a very concurrent or very in a high throughput environment, this gets very slow. Yeah. So the idea is like, well, the slow part is عندي كل file ولا كل page file. The problem is like I'm going through all the page files باش نلقى واحد الكey. Well, what I can do, since I'm the one that I'm storing keys in those files in the first place, I can have like a global view of all the keys and then know about all their locations in a given page file. Right? So it's like I can keep an in-memory on disk map, sort of a key, which is the key that I'm probably looking for, to the location, which is an offset in the file and then the file itself. So فاش كتجيني دابا get request, I don't go look through all the files. I just look in my map, find the actual page, and then just go read the page directly, since I know the page in the offset. Mehdi, makes sense, right? Some storage systems would even like have like this on a multiples of levels, because like this index wouldn't be like super like this. If the database is big enough, like this index can't fit in memory, which is like one of the the biggest selling point in memory, so it's very fast to access, but you can also persist it. Some storage systems, what they will do, they'll store a small version of this index just for that specific file, and then they'll store it in the header of the file. So باش ما نحل الفايل ونبقى نقرا الفايل كامل باش نعرف كاع الكيز اللي فيه, I'll just have to read an index of this file, and then from there I'll know فين كاين الداتا ديالي on that file, and I can do a fast check whether this key exists or not, and if it exists, where can I find it? Some other storage component will either like store like other probabilistic data structures that are easy to store, like they're super great to compress. Well, they can do a very fast lookup of whether a key exists or not on this, to act as like this first read, add باش نديرو like the second read. There are different ways of doing this, but like the most generic form of this is that we have some data structure. It's either stored on disk, like in memory. We want to read some key because we know like a query plan that هنا عندنا شنو, and we determined that we need to read this key for this value. And the way to do it is like go through the index and then make it fast. So فاش كدير انت create an index, the database engine is actually doing something like this. Well, the colon is the key and the value is the actual tuple location on the file. رضا.
ولكن دابا the problem is الا كنت انا غادي المهم حيتاش what you explained بان لي زعما what's different between الا درت انا مثلا واحد لقيت باي let's say واحد الاي جي ومشيت قلبت في الداتابيس ديالي بداك الاي جي ولا بالاي جي وبشي فيلد, وبين الا مشيت قلبت بداك الكي ياك اونتوكا غادي نمشي نقلب بداك التيبل ديالي زعما الحاجه اللي ما فهمتش انا في الاندكسين هو what's so special about it زعما علاش هي
I never said it was special, right? So إلا عندك هاد الكي هادي تقدر by default every table for your database have an index on the key. Yeah, so you can like looking up things by a key is very fast. إلا قلتي له أعطيني select where the ID is 1, there is an implicit index here that can go and to know that key ID 1 كاين ستوري في هذا الفايل هذا في offset 3. تصير قرا من 3 غتقرا الفاليو. I don't have to do lookups, right? If I wanted to make an index over this table for another key, I can make it. Does this make sense? Or can you repeat the question? Maybe I can explain it better if it doesn't make sense.
بالنسبه للاي جي يوسف زعما كل اي جي باي ديفولت عنده واحد الكي, ولكن زعما بالنسبه للفيلدز الاخرين اللي ما عندهمش هذاك الاندكس مثلا نيم ولا شي حاجه اخرى اللي ما عندهاش نيم, دابا البروبليم اللي كاين عندنا اللي كيحلوا الاندكس هو هذا الاوفست هذاك, ما نحتاجش نقرا الفايلز,
ما تحتاجش في تقلب ما تحتاجش دير linear scan through all over the files اللي كاينين ديال داك التيبل. all you have to do غتمشي مقصد. الا ما عندكش اندكس خصك تمشي تقلب بيديك.
Thank you. Yeah.
Okay.
Ça marche.
Azouz.
Yeah, but indexation is kind of like a concept in general. ماشي بالضرورة in storage. Usually when you have data, you can write, like you can implement a lot of indexes just on that data. You can have an index based on the name, you can have an index based on the ID, you have an index based on the, I don't know, birth dates and such. And then you can use it to make searches faster, basically, right? In general.
ماشي هادشي اللي قلت انا ولا قلت شي حاجه اخرى؟
Yeah. Summary.
غير باش نتاكد كنت قلت شي حاجه اخرى.
Yeah, cool.
All right. Any more questions about indices? Indexes. Much no الجمع. Okay. إلا بانوا questions اخرين سولوني. We'll go to yet another more generic term, which is a cache. An index is a specialized cache for storage systems, which is usually used in storage systems. A cache is just a cache, which is a software component that relies on the locality of reference principle. شو اللي مرة اسمها locality of reference principle؟
انا ما سمعتش ذاك الشيء.
خليه يسمع.
شرح لي انا بعد.
زعما انا عمري سمعت.
انت عمرك سمعت. Well, like computer scientists are شو نقول لكم, like they make the most intimidating names ever. They make, for the simplest things, they will come up with a name that is super weird. So locality of reference principle is just like that data اللي تخدمها دابا is more likely to be accessed at a close point in time. So إلا قريتها دابا I'm more likely نقراها من هنا 5 ديال الدقائق أخرى. And this is why like warm caches are important. Data recently getting accessed is most likely to be accessed again. That sort of thing. Which is like a very simple aspect, but in practice it works very well. Right? And that's why caches in industry work very well. So كان شي حاجة very popular, like anything that you can think of that gets very popular at one given moment in time, if you cache it, since it's very popular, people will still be accessing it at the same time, and you get a lot of value from caching it in the first place. And this applies to everything, like web servers, any hardware, like CPUs and operating system, like caches. Everything else relies on this principle, and it's just like very, and in essence, is like very simple. If you have like any computation, generic computation كيما بغيت تكون, you wasted the compute power. The computation has to be pure, i.e., I can define it as a function of inputs that'll always, as long as the inputs don't change, the output would stay the same. If I have this function, which is my computation in this case, I can store the value or cache the value, and then hopefully the next time I'm gonna be asked to get that value of that computation, I'll be able to just retrieve the value from the cache. This was also beneficial, assuming below computation ماشي هي 1 زائد الvalue نتاع البارامتر, because that will be just wasteful, because the computation could be done much faster than storage access itself. So if I make any sort of computation كيما بغيت تكون, like I have a client that want to get the cache value, I can read the value from the cache for that specific operation. Let's say I identified by key 1. If I can find it here, I know that the value exists and I just return the value. Otherwise, if I don't find it, I just perform the compute. كندير ذاك الاوبريشن شنو ما بغيت تكون, like request perform a network call, like crunch some numbers, ما شغلنا شنو بغينا نديرو, and then I give it back to the client. And then the client can be smart, and then the strategy would like be just write this value back to the cache. So that المرة الجاية فاش غيبغي شي واحد آخر يأكسد لها, will have access to the result pretty much computed. Caches are usually implemented in a way that this since هادشي هذا you can think باللي يقدر يكبر infinitely. They have like eviction strategies, which is usually implemented in all major. It can be implemented cooperatively, like we can rely on clients to clear things out when they no longer need them, which in practice doesn't really work very well. Well, we can implement it as background processes that perform the eviction depending on a bunch of eviction strategies. For the case هذا, I mean, there are a bunch, FIFO, LIFO, LRU, MRU, it doesn't really matter. What matters is that an SM use case, and we know مثلا باللي we want to keep the least recently used. So كاع هادوك اللي تقاسوا دابا ما عاودناش اكسيدين لهم in a while, they'll be evicted and will be cleared out, and we can reuse the space to like cache new things. وهكا we keep the cache alive. I guess like there are like other strategies about like how do we write. في هاد case هذا like I wrote the client will that the write back to the new value, but it can be that the case that the cache itself knows how to fetch the value and write it back before returning it to the client. So when you do get cached, if it can't find it, the cache system would know how to perform the computation and would know how to store it before returning it to the client. أنا هنا ما جبت حتى شي سمية ديال a cache system. You can think of Redis, Memcached, or any caffeine. There are a bunch. كاينين بزاف حيت كاين other. They can be standalone. They can be embedded. They can be just like some sort of map in memory that you never see, but they all considered caches, and they are usually البرنسيب كامل واقف على أن the whole concept is I'm gonna exchange cheap memory for expensive CPU time. That's the whole idea. Nizam.
And something that is critical use caches, like let's say banking applications. Would they use cache, or would they query the database every time they want new information? Like if you've ever worked on something similar to banking.
Let me revert the question back to you.
Oh.
Why wouldn't they be able to use caches? In a lot of use cases, it'll make sense to use caches, but in some of the use cases, it doesn't make sense to me to use caches. I'll leave you to explain which cases doesn't make sense and تخدم cache.
If you're looking at account balances, I don't think you can use cache. And that's the only use case I was thinking of, honestly.
So what's the point of storing of cash in account balances? شنو غيكون الربح ديالك إلا بغيتي تكاشي account balances؟ بحقاش ماشي we can't really say that every time just slap a cash on it and it'll be good, because that's not really good design thinking. You should think about like شنو غتربح من داك الكاش. في الكيس نتاع let's take a banking application that want to store account. Their accounts are stored in a relational database that has a bunch of like, I don't know, gets provided بزاف نتاع ACID semantics, which we want because these are user data that is critical, it's replicated, and it's important that we want it to be consistent. And then I can slap a cache on it and just read the data from the cache. And then if I do this and the data is stale, I can potentially lose money either for my clients or for me. And the speed up, the speed up itself is not important. ما تربح تجي حاجة speed up. Like if you access like one single row every time from a database, you're probably better off and like just read it from the database, especially if you care about consistency. Databases are very fast components, and it's rarely is worth it. And like your SQL databases, you can to stick a cache in front of them, unless you have a lot of read-only operations and your system is not highly mutable. But that being aside, like banking systems like employ a bunch of other crap to make the data consistent, and they can get some decent performance out of it. Especially حاجة أخرى, like have you ever seen a banking application that is actually fast? Most banking applications are not fast because like they don't optimize for performance. They optimize for consistency and reliability. They don't really care about performance. And you wouldn't care about performance either. As the customer, you'd rather انك تاخذ الفلوس ديالك in 30 seconds than just wait 1 second and then potentially lose all of your money.
Yeah, understandable. I didn't think that maybe it's not important to cache it. Yeah, good. You make a good point, I guess.
Any more questions about caching? Also, like, if you don't get anything out of Google file system, it's fine. It's totally unrelated. الناس اللي خدامين في Google don't really care about it. And they don't really need to know about the details. But this is super important. And I'm assuming like حضرنا على caches at some point. So just a refresh. Khalid.
Between ajouter l'idée, cache can be used to save on bandwidth, not only compute.
There is true.
server تقدر تستعمل local cache في file system بلاصة ما تمشي web server.
Yes.
Yeah. Browsers.
Yeah. That is true. I was thinking of another use case of storing bandwidth, but you have to be very big to care about bandwidth for that stage. But yeah, you can if you think about like just browsers and browser caches, they are very good on saving bandwidth. Any more notes? Questions? Is caching considered to be secure? I don't understand the question. Can Can you elaborate, Anwar? Can you speak up? It'll be easier. نقدر نريكوردك. All right. En attendant le job, let me move on. All right. I guess like this is another thing اللي هضرنا عليه من قبل, which is what a leader-follower scheme look like. These are usually like we have a system and it's kind of replicated or distributed, and you want to do coordination. Well, I guess like last week هضرنا على consensus, and we said that this is a model that kind of like help with having automatic re-election of this leader, and this wasn't and isn't always a necessary aspect of your design. A lot of systems will just have like a leader elected at cluster bootstrap. They would say and bootstrap واحد الكلاستر ديال ماي اس كيو ال ولا ديال بوستغريس ولا ديال X. We're gonna mark his system as a leader, and then I'll create a couple of servers, and then I'll tell them that guy is the leader, just sync from it, and you are just followers. That'll be it. The followers wouldn't have to think about anything. The component كيطلع فيه شي flag اللي كتطوق لي follower mode, where it doesn't do anything that a follower shouldn't do. So it understands semantics into a follower, so it shouldn't accept rights. It can delegate rights to the leader so that it knows what it does with them, but it doesn't accept rights and only just send you reads. And the leader is responsible for doing reads and writes and accept and like an acting writes and responding to reads. And most external systems would just really just know about the leader. And the leader would just take the proper decisions about this is what means that the cluster is healthy, this is what it means that the cluster is out of capacity, or this is what it means that I'm not healthy, or anything else that is cluster based. All right, Anwar, go for it.
تسمعني؟
Yep.
Ok. La question كانت واش الكاشين is considered to be secure. I will give an example. Let's take an e-commerce website اللي فيه user's account balance. So after the user login, the website caches the account balance for a short duration باش improve in response time. Okay, the scenario اللي طاح لي في بالي هو if an attacker manages to gain واحد l'accès temporaire l'utilisateur, le compte utilisateur, المهم by phishing ولا other ways, هاد attacker might be able to exploit the cached balance information. باش نelaborate هو بحال دابا attackers might be able to access the cached balance information even if they haven't successfully logged in. حيتاش caching mechanisms often rely على simple authentication methods compared to the full login process اللي يكون more secure. That's زعما الايديا اللي كانت في راسي وما عرفتش واش صحيحه ولا لا.
To be honest, I'm not an expert on security, but I would say like caching is as secure, like in this context, like caching is as secure as the medium that you use for caching. It عندك a very weak medium for storing anything, like as long as that even for actually the medium, like you're open to any sorts of attacks. So you're looking to, and also like in this case, I don't know, it kind of depend on it's on a case by case basis. If you just store something اللي ما خصكش تستور ولا ما خصكش تكاشي in the first place, you're opening yourself to a pothole of attacks as well. محمد شفت حليتي الكاميرا بتقول شي حاجه؟
واحد الحاجه اللي كنت بغيت نقول هي مثلا في هاد الكيسز we need to define ديما واحد اش كيتسمى واحد تريت بلان، فهمتي؟ شنو ولا واحد الثلاث سيناريو اللي زعما بغينا نهاندليو باش الا غنعطيو مثلا ميتيغيشنز ولا تكونوا في نفس فهمتي في نفس الانفايرمنت. هنا الا كنا يقدر الا كنا اوبن بحال هكا راه ايفن ذا اوبريتين سيستم يود تراسي ايفن مثلا الا كنتي كتستعمل شي نو شي تراستد اكزيكيوشن انفايرمنت بحال انتل اس جي اكس ولا ارم تراست زون ولا شي حاجه اللي اصلا باي هاردوير كيسيكيوري والستورج you might again say okay كاينين شي اتاكس اخرين سايد شانل اتاكس etc. I think كما I agree with you مهدي the security ديال مثلا الكاشين itself is as safe as the actual medium او لا. Another thing I would add, it depends on the implementation ديال الكاشين ديالك. مثلا let's say we are using Redis and we know like مثلا كاينه شي vulnerability في Redis. For that yeah like you would expose data ديال users ديالك because the underlying software اللي you are using for caching is vulnerable. اما مثلا الا كان ريديس مهوستي في شي بلاصه ومهوستي عندك والاتاكر اصلا عنده الطلاكسي مثلا لاكسي الميموري let's say it's hard that حيت كيكونوا protected regions it's hard that the attacker can read that chunk of memory unless كما قلت لك كاين شي vulnerability في Redis itself. I hope I clarified the point. I hope I didn't make it more confusing.
No,
At least.
actually, thank you for the clarification. You
مرحبا.
said that the implementation زعما داك الانترميديات implementation هو اللي خصنا نتكونسونطراو عليه اكثر ما نشوفوا الريست ياك.
Yes.
Yeah.
حيت غير كتحاول تليميتي مثلا الاتاك غيوقع مثلا انا كندير واحد الاسامبشنز على الاتاكر كندير واحد الاسامبشنز على السيستم ديالي كندير الاسامبشن على السوفتوير ديالي عاد كنحط اتاك بلانت فهمتي. ما يمكنش غير زعما حيت الا كان غير اوبن بحال هكا على الاقل كيكون عندك واحد سيكوريتي اسامبشنز اتليست مثلا يو تراست ذا اوبريتين سيستم في هذه الحاله then you can discuss the other stuff.
شكرا سي احمد. شكرا سي مهدي.
Right. Thank you, Sihmet, for your answer.
الله يحفظك.
Any questions about leader follower scheme? I feel like هضرنا على leader follower scheme is enough, like as part of the consensus week. We spent probably like 40% of or the 50% of the session ما هضرناش على GFS كاع, which is great. Okay. شكون اللي ما عمره سمع heartbeats؟ I'll go ahead and explain things, and then you tell me if it doesn't make sense. So heartbeats are special messages فاش كيكون عندك distributed systems that tell you عندك like a leader follower scheme, like would ولا even any leader follower scheme, like إلى الليدر بغى يعرف شكون هما الفولورز ولا بغى يعرف فين كاينين ولا بغى يعرف any information يعني are they still responsive, are they still healthy, can they still handle writes, can they still handle reads, can they do anything. You can make this as part of like the heartbeat message. These are like periodic messages. صراحة they can be implemented in two ways. In a model where capacity can be added like on the fly without the master even knowing about it. Once you add capacity, you spin up the new followers. The followers have to register themselves with the master. And this is usually done by a special message which can act as a heartbeat or a liveness check. You just sign up, you just tell them where the master is and they sign up to the master. Or they ask one of the nodes, where does the master live? And then I can talk to the master. And then periodically they can send data to the master about their current state. The master's responsibility is to compile the data and then knows which servers are available, which are not. And then مثلا إذا ما جيتيش كل 10 دقائق مثلا the leash is like كل 1 minute, say كل 1 minute I have to send health ولا a heartbeat. If there's 1 minute and you didn't send me anything, 2 minutes and you didn't send me anything, I'll know that that follower is down and is unavailable, unresponsive, and then I can raise an alert. I can pay somebody. I can stop accepting requests because I don't have a quorum anymore. It doesn't matter. I'll have to do something because now I know about it. And this is great because it helps with timely mitigations. Like a lot of like server or crash failures. You know that if you have like continuous heartbeats actually going on, once you stop receiving heartbeats like from a bunch of servers, you know that these servers are down and there is something actually going on, and then you can have a human look at it. Another way is that when the master actually connects to a third-party component, like in this case, and the master and Ghanaian nodes, we can have like a third-party component where the master connects to, and then it could get all the addresses about all the other followers, and it can scrap health metrics through all of those. And then anything that can't report the health metrics, and not alive or not well. And we can, from there, like perform the same operations. I do my heartbeats. Like they are just special messages. In most applications, it's just some endpoint over TCP that returns okay. And some other systems, which I've seen that are more elaborate, that they can return all sort of metrics that you can scrap. And they can even like check consistency and state of their internal application and return it to the master, which will do something with it. Okay, I guess heartbeats are to some extent obvious. If they're not, please feel free to ping me later. Okay, we'll talk about leases. Leases are distributed in distributed systems. A lease is like, let's say, think of them as locks in normal programming, where we can have like بزاف نتاع الكومبوننتس اللي كيكومبيتيو for performing a computation, writing a value, anything that'll require those components to actually compete with each other. We can force them to and we just want to be able to mutate that value. We can have all of them like compete compete to get a lock. هذا الشيء هضرنا عليه ذاك المرة for like consensus as a service. فاش هضرنا على consensus overall is that you can use a consensus system or a consensus distributed state machine to implement a distributed lock, and then everybody could just compete to take that lock, and whoever takes that lock have exclusive access to that value. The problem with this, with most systems that actually behave like this, is that if you take that lock, you have exclusive access to that particular resource or computation model. And then if you fail in the middle or you crash in the middle, there is no way that anybody else would be able to use it because you never released that lock. So every lock like you get, you'll have to renew your lease as long as you are using it. And if you're not using it, you don't renew the lease. And if you don't renew the lease, you have crashed or something is wrong. And in that case, we can give other locks to other users, or at least we know that this lock is actually needs to be dropped, right? So the whole point is like we want to make sure that resource access, whatever it is that we are protecting through this lock, is bounded through an amount of time. We don't want it to be like infinitely given to you. You can hold it infinitely if required so, as long as you're renewing the lease. So that means that you're well and alive and you're actually doing something with it. But just having the lock and crashing without actually releasing the lock or telling anybody know that you're dead, that's not great. All right. Checksums, this is not a distributed systems thing, but this is like more of a storage thing, which is like this stems from the fact that we don't really trust disks and networks with the integrity of our data. Bit flips happen everywhere, and just a bit flip can like turn your balance account from 0 to 2 to the 10 in a minute. So if you're storing something on disk, it's important that you actually, before you store it and before you transfer it, you should also store like some sort of checksum, either a CRC or an MD5 hash of the given content that you know is true. And then whenever you can always verify that the content that you actually have or read is the actual content that you've written by just performing the reverse operation. Just do the CRC or the MD5 check, and then perform the equality check between both hashes. These are not cryptographic hashes. They are just simple, like linear, like very easy to compute hashes of any sort of like byte information, which makes them like pretty cheap to do in most systems. I'm going very fast today. We are running out of time. But if anything else, please Habsuni. Same thing in networking to check the integrity of a packet CRC. Yes, that's correct. All right, a wall, which is like a very popular term for storage systems, which is write-ahead log, which is like this component that is usually used to record a log of all the operations that change the system. And this is important to protect against crash, to provide crash safety. Which means إلا قطع عليك شي واحد الضوء, right, على ذاك السيرفر اللي انت فيه, and you committed a write, and you told the like you have a client, right, and he says write key value, and then you get it to the master. The master needs to write it to, I don't know, some file somewhere over the network, and in the meantime, right, you crashed and you wanted to restart. The only thing that is actually considered written are the things that are actually committed are the things that are not after the watermark and the wall. So أي حاجة كان, like every log has like some watermark هنا اللي كتقول له okay I applied قاعد داك الشيء اللي هنا والفوق, and then everything من الwatermark اللي تحت is actually new. So the same thing, the moment كيجيك a write operation كيما بغات تكون, you just add it to this wall and then start performing it, right? And then afterwards you just tell the user that the operation is actually performed, and then you move the watermark. So when you crash, if anything happens and something goes wrong, you can rebuild the state by just going through the log of operations that you haven't really performed yet. All right, phew, that was a lot. I know في الآخر جريت شوية على دوك الثلاجة, but like we have a couple minutes and I wanna talk a little bit about GFS. داك الشيء الآخر إذا ما كانش clear, please leave questions. If you don't leave questions, you'll still have the slides and you still can ask questions من بعد. All right, the Google file system. This is a case study. This is not by any means, I know the course is called Distributed File Systems, but we had to pick one to study it. And then later on I'll give you like the homework to like make the comparison. So GFS, which is the Google file system, it was designed and published, and Google published a paper in SOSP in 2003. It was one of those large distributed systems that actually works, because a lot of people came up with papers about theoretical models that may or may not work in practice. Google in 2003 already had like a large amount of data that actually used GFS. So they presented it as a case study about like what is the performance that they got out of their design. And at the time, they had like a bunch of logs through all the developers and production systems, and they had all the crawlers that like crawl through the internet to scan and index websites, and all those like stored petabytes of data into the file system, and they published their design to see how did that work. When they were like in the design phase, they considered scalability. They wanted things to scale. They wanted to be able to add resources, commodity hardware easily. They didn't want to have to run it on special hardware, and they didn't want like downtime to perform maintenance or to replace disks or whatever maintenance operations. They didn't want to have like downtimes to do this. They wanted to maximize throughput. They didn't want to have like a leader election in the middle because that would cause some throughput operations. They didn't want to like have like writes go through the master, as we'll see, because that will hinder the throughput of the system. They made a lot of compromises to make throughput as big as possible. They implemented it so that it has like that most of the writes are going to be like sequential. So most writes that will come to the system, since these are logs, which are mainly like sequential, and all the indexing data is, for the most part, was at the time sequential. And it was optimized not to work with small-ish files. They optimized it to work with large-ish files, like of megabytes, and millions of megabytes files. And they wanted it, of course, to be fault tolerant, and you know what fault tolerant means by now. The API that the system provided was like a POSIX compliant file system. Although it didn't go like through the standard open read-write syscalls that standard Linux file system would operate, it came like with a thick client library that provided create, open, write, read, and close, and delete operations. But this is pretty much all what it provided, like standard file operations that you can perform, and they wanted it to be similar to what our developers are actually used to through the C and C++ standard library. Okay, so this is like a simplified view of how our GFS cluster architecture look like. We have these clients that live somewhere, and you have like the GFS cluster, which contains which has like one master that stores all the metadata about the files and the file hierarchy in the cluster. And then it has like some amount of chunk servers. These chunk servers are the ones responsible for storing and serving the data, and they register themselves with the master, and they report health checks and metrics to the master, as shown before, like as part of like their heartbeat messages. And you can add capacity to the cluster by just adding more machines and making them register with the master. The client can read and write from any files that they want. They would send a fetch metadata. They will try to keep the local version. The client again, like it's a thick client, which means like it has a bunch of logic, just like a thin client that doesn't have anything in it. It has a bunch of storage and a local copy of the master's metadata, and it tries to keep the metadata. It is in sync with the master. And whenever it wants to perform a read operation or write operations, it just getting the metadata would give it like all the files hierarchy. And then if I wanted to read a file, I'll have to talk to these chunk servers, because the data for those files will be stored on those chunk servers. So I don't need, on the read or write path, I don't need the master. As long as I have a fresh enough copy of the metadata, I will be able to perform read and writes. Because all I have to do is like reach out to these chunk servers and just read the chunks and then construct the chunks to make the file. Okay. So how do these chunks and chunk servers look like? So we have the master itself has have this file. Like let's assume that the master have like these two files, like home f1.txt and home wallpaper.png. Every file is actually decomposed into multiple chunks. And the master would keep, like in this case, like home f1 has like 2 chunks, wallpaper.png have 3 chunks, and then each chunk, let's say, is of equal size. It has like 64 megabytes, and each chunk is usually replicated to 3 chunk servers so that we survive like some chunk server being down for maintenance or like some disk burnout. So let's assume master, like if you told it, give me the metadata about the cluster, it'll tell you that I have 2 files, one called /home/f1, and it has 2 chunks, and these chunks actually live, chunk 1 lives in chunk server 1, chunk server 2, chunk server 3, and 2 lives in 1, 2, and 4. And you can see them color-coded here. Like C1 has chunk 1 and chunk 2 from this file, and it has 4 and 5 from this file. This one has 1 and 2 from this file, 4, 5, 6 from this file, etc. The way it was designed is such that if we need to extend or need to change this file, we don't. These things could have all different shapes and capacities, and as long as they have like 64 megabyte slots, we can still store things into them, right? So once you have this information, you can see that it's pretty easy. I just have to contact, like, say, for this one, I'll talk to C1 and tell him to give me like this chunk. And for this, maybe I'll talk to C2 because like I'm already talking to C1 for this one. I'll talk to C2 for this one. And then I'll be able to get my 2 chunks, and my 2 chunks would make my file. All right. The metadata is stored in both volatile and non-volatile storage. Like the hierarchy and the chunks to file mapping are actually stored on disk, and they are replicated through the logs. So whenever chunk mapping changes, the master needs to know about it, and then we need to keep track of it as part of the internal storage of the master. The chunk replicas, since they change, we can always rebuild. They are stored just in memory, and then whenever we do another bootstrap or we restart the server, we can just restart them by, once the chunk servers actually register, they will send you like who are the where are all the chunk replicas as part of their heartbeats, and then you can rebuild this information. But these things are actually necessary for the master to be able to perform its operations, because the chunk servers don't really know anything about the directory hierarchy. They just store blobs of data. Only the master knows like that this blob of data actually makes file/home/wallpaper. But these actual chunks don't know what they are storing. They're just storing like series of bytes, for all that matters. And again, like the mapping from /home/f1 file to like chunk 1 and chunk 2 is actually only the server would know about it, because again, like these guys don't know about the files at all. Like the chunk servers only know that they actually store chunk number, I don't know, 1602, and they would report this to the master, and the master would have that mapping from chunk 1602 actually is mapped to as the second chunk of file, I don't know, file f1.txt. All right. So there are a couple of questions that comes to mind whenever you look at the design. Is what if the master crashes, right? Like in the design we did earlier, in this guy, since this is the only component and there is no master election happening, whenever this master crashes, what should we do? What happens? This usually translates into, if this master crashes, we just have another shadow master that is sitting around and just monitoring it, right? And periodically just syncs the metadata updates that are happening to the master. It just syncs them towards it. Makes a snapshot of the metadata and just syncs it. And then if this thing actually crashes, we would know about it, and we just register, like we will have like our cluster, the cluster manager system would just change this master for this master, and then we would be able to like tell the chunk servers to actually re-register with the new master, and then we will have a recent enough copy of the master's snapshot, so we are to some extent up to date, but there are still some operations that we haven't really put into our internal storage, and that's why the master keeps a wall, as we saw earlier, of all the operations that it actually performing. So if it crashes in the middle, we can still reconstruct the state that we actually want. And that's why we are able to, for snapshots and the wall that the master actually keeps track of, are key to actually reconstruct the metadata fast, so that downtime is minimal. And at the same time, like if that in that window where we have a crashed master and another bootstrapping master, clients can still read data because like they have a recent enough metadata, so reads are still actually can work because like they have the mapping cached locally, so they can still, even though they can't reach the master, they can still reach and create chunks. They can still reach and read information from the chunk server. Right. So let's dive a bit deeper into like read operations. So most read operations would go like first, like I want to read a file, and I want to read the chunk ID 1, 2, 3, 4, any chunk ID, and the master would give me like the chunk information, as in like where does it live, which file on the chunk server, and which chunk servers is it replicated on, and then I can perform my read operation over the chunk ID. Given the chunk ID, contacting the chunk server, and then giving it like a byte range that I actually want to read. Because assuming I don't want to read all of it, I'm just gonna read the range. I'll just have to give it that information, and the chunk server will just give me the bytes that I want to read. The write operation is like we need to get the file metadata, and then get the file metadata back, and then that file metadata, it should be written should be sent to all kind of replicas where we want to store that file. And then once all of them acknowledge that they are actually available for writes, because they write all the data into like temporary files, or temporary, think of it as a database two-phase commit. We will send all the data, right, as the third option to all the replicas where the file exists. And then once all the data actually reaches the chunk servers, and we make sure that the data is properly replicated through all of them, we'll just send an acknowledgement or a write operation, right? We will tell them, hey, now you can commit that information now that you have it. And that's why we can guarantee that data that is marked as being written is actually written through all the chunk servers. And if any of these operations in the meantime actually fail, we just have to retry until all of them have the data, and then we send the write operation. So all these operations are protected through against corruption by performing all the chunk files are actually checksums, and the checksums are actually stored within them. If any of sort of funny things actually happen, we will detect that there is a corruption. We will take the server out of commission, and then we'll send the master. We'll probably send master information that this is actually going out of order, and we'll need another chunk server to actually copy over those chunks. Garbage collections are usually like if we can delete chunks, but this is usually like lazily recollected through like background processes that will go and like scan chunks and find which chunks doesn't actually correspond to any of the files, and then delete them later on. And this is to allow for, if we mistakenly deleted a chunk and we wanted to reclaim it, as long as it's there, we can just reattach it to an existing file, and we won't delete it. So we want to give ourselves or the people who maintain this like a bit of leeway and be able to remake that link so that we don't lose the data required. All right, this is pretty much it for GFS. I covered most of the architectural choices and a bunch of like the decisions and the read and write paths. I know I've went through this like very quickly, but that's why I knew I'm gonna do this, because like this is gonna take, the first part is gonna take, I think is very important, and it's gonna take some time, but we'll still leave you with a bunch of homework to do. So hopefully the homework will help you understand some things better. Are there any questions about this قبل ما ندوز الhomework? Going once, going twice. Okay, كل شيء كيصير له homework. Okay, so already like 20 minutes at a time, so I'm gonna go with the homework. The homework itself is just I'm gonna send you a couple of links to Discord. I want you to read 2 papers. The first paper is the GFS paper, which is the one that I used to make the slides. So ideally the information اللي غتقراهم في GFS paper هي what's actually explained in this lecture, although in a bit I skimmed over a bunch of details that are mentioned in the paper, but the gist of the design that you need to understand is the thing that is on the slides. So this is paper 1. In paper 2, you'll have to go through the Ceph paper. And the Ceph paper is another file system that is open source, distributed, also claims that it can infinitely scale. And it provides like 3 sort of like client or APIs. It can perform like an S3 compatible API to be used as a blob storage. It exposes like a block storage API to be used like a block device or a virtual block device on the Linux file system, so that you can mount basically another file system on top of it. And it provides like a file-like API. So I want you to read through what makes this actually work in terms of like the design and architecture. I don't really care about like the different APIs that it exposes, because like that's not super relevant to the distributed systems course. What we care about is like the architecture and how can this survive failures? How can it guarantee consistency? How does it react to the CAP theorem, and how does it like work with the CAP theorem? Is it like an AP or a CP model, or and how does it compare to GFS? Just from the data that is mentioned through both papers, can we make a comparison about like what are the design choices that were made through different aspects between GFS and Ceph? And would you say that one did it better, or one is inspired from the other or not? Also, like Ceph code is open source, so you can like just go and read through it easily if you want to. Any questions? The homework itself is just, and the next week, please bring, everybody should be able to have like a page or 2 about like the difference between differences, similarities that they extracted by reading both papers in between the both systems. If everyone should send it to me Discord like before the next week, so that we can review it and then we can see like whether we can extract some similarities between analysis leaders. That's pretty much the homework. And of course, I'll send you the links to the GFS and the Ceph papers, so that you can easily access both. Today I learned about Ceph. Yeah. Any questions, notes before we close off?